Hi, my name is Resul. Welcome to this presentation on two-dimensional force systems or planar force systems. We'll cover the following: moment of a force, the principle of moments, also called Resultant's theorem, and an example, force couples, equivalent couples and force couple system, and an example, the line of action of a resultant for force couple system, and an example. Let's get started. So a force, the moment of a force really is the rotational tendency of a force. It's also called a torque. It's defined in two dimensions at a point, but in three dimensions we can define it both at a point and also on a line. So this is our illustration here. So we have got this force F, for which we want to calculate its moment about the point A. So how do we do that? We calculate it by multiplying the force F with the perpendicular distance, or the shortest distance between our fulcrum A and the force F, which is this D here. So MA is in this case FD, or FR sine theta. If you use this distance as not perpendicular, R, so R sine theta, which is the same as D times F is our moment. So this R sine theta reminds us of the cross product. So we can say the moment of the force F at A is simply defined by R cross F, where this R can be any distance. Okay, from A, the R can be this one here, or the R can be there. It doesn't really matter. It's defined basically by the cross product, and the angle theta takes care of the moment in this case. So the sense of rotation, what we see right now, if you look from the top, it's counterclockwise. Okay, so for the algebraic method, it doesn't really matter. So counterclockwise is like this. But for the vector method, the counterclockwise is positive and the clockwise is negative in the right-handed coordinate system. Okay, that's what we see here. So now let's look at what is called the principle of moments. Now scientists are famous for taking something simple like the principle of moments and give it a complicated name that like the Resultant's theorem. But let's see what it says. So the moment of a force about a point is the sum of moments of its components about the same point. So we have this force R, and it's got components Q and P. So the moment of this R about this point O should be the same as the moment of these components Q and P. Now why do we do this? In most cases, problems that we calculate in mechanics are easily figured out by looking at components rather than the force itself. So that's why we split it up into components and take moments of the components. So in this case, we see that the moment at O of this R is simply R times R, this R here, which should be the same as Q times Q minus P times P. So we've got a color code here to see what the forces are and their perpendicular distances. So let's look at an example. Calculate the moment of the forces and couples shown in the figure about 2 points A and B, and this is our figure here. So we calculate about this point A and also about this point B. So about the point A, if we take clockwise as positive, then we're going to get 100 times 9.81 times this distance 3, okay, minus 150 times this distance 2, minus 150 cos 30 degrees, which is this vertical force here, okay, times 3 plus 2 plus this distance, which will be 1.5 sine 30 degrees. And then this component of the 150 that's going horizontal, it will be plus 150 sine 30 degrees, and then the distance we're looking at from there to there is going to be 1.5 cos 30 degrees, which is what we see here. Okay, and since we assumed clockwise as positive, then we say plus 200. The 200 here is a free vector, so you can place it anywhere. You can place it there or there. It doesn't really matter. You just say plus 200. And then once we do the arithmetic, we find 2193 Newton meters clockwise. Okay, and then moments about B. First of all, we notice that the 150 Newton force here goes right through B, so We don't need to calculate it because it has no moment about p. Okay, and then if we take counterclockwise as positive, then we'll have 100 times 1.81 times this distance d. Okay, and then plus 150 times this distance 2 minus 200, because the 200 now is counterclockwise. Then we get 2062 Newton meters. Okay, now what is a couple? A moment that's produced by two equal and opposite non-collinear forces is called a couple. Now let's see what it is. So in this case, we have this force F, okay, and then F separated by the perpendicular distance d. So how do we calculate the moment of this couple here? Okay, so the moment about this point P will be this F, okay, times A plus D, okay, minus this F times A. And when we evaluate this arithmetic here, it should give you FD. So the moment about the point P is FD. Now this P can be on this side of the F, or it can be in between, or it can be on this side. Doesn't really matter. The moment will be FD. In fact, another simple proof to prove that it's FD is if this point was at this point here, okay, or at this point, either of these 2 points, then the moment is simply FD because it eliminates the force where we have calculated the moment. Okay, now let's see if we can do the same thing using vectors. So the moment about the point O, okay, we're going to take RB is the vector from O to anywhere on the line of action of F, this first F, and then RA is the moment to anywhere on the line of action of A, okay, and then of course RA minus RB is this R here. Okay, so we can say the moment about O is RA cross F is RA cross F plus RB, okay, cross minus F, because this F is going to go opposite to this one. Okay, now if we put our terms together here, then we have RA minus RB cross F. Then this is the same as R cross F, because RA minus RB is R. So this is the same as R cross F. So the sense of rotation here is clockwise negative and counterclockwise positive if we're using the vector method in the right-handed coordinate system. So now let's look at what's called equivalent couples and force couple systems. So which will be described by the same moment vector that we just saw. It will be equal to FD. Now if we have this F and F separated by the distance D, and we take half of D, then of course if we have twice of F, it will be equivalent to what we have before. So twice of F and half of D. Or if we double D and half of F, then we have 2D and half F, and that is equivalent. So all these three systems here are equivalent. Okay, now let's look at something that's important in mechanics, where we replace a force by an equivalent parallel force and a couple. So let's see how it happens. So with this rigid body here, and there's a force F at A, and we want to move this force to this point. Now because we are moving this force to this point, it's going to create a moment, okay, and a couple at the same time. So we have this F, okay. So what we do, we place this F at B and then in the opposite direction. So what we have really done is equivalent, because this F cancels this F here. Okay, but when we realize that now if we do that, then this F and this F, they create the couple, which is equal to FD if you use the perpendicular distance. And that's the M equal to FD. And then this remains F here. So what we have done is we have this single force that has been replaced by a force couple system, which is shown here. Let's look at an example. Replace the 150 Newton force through point B with an equivalent force at point A. So we've got these 2 points A and B, 5 meters, 30 degrees, 150. So we take this 150 and place it here and also in the opposite direction, like so. Okay, and then we look at the perpendicular distance. We look at the line of action of this and the perpendicular distance that gives us the distance D here, which in this case is going to be 5 sine 30 degrees, and we multiply by 150 because our moment is simply FD, and then we get our answer as 375 newtons. And then we have moved this 150 to A, and then this moment is 375 newtons. Let's look at what is called line of action of resultants for force couple systems. So we have a bunch of forces here, F1, F2, F3, okay, and there's a point where our point that we're interested in to find the resultant and the line of action is this point or here. So this F1 creates a moment F1 D1, and F2 creates this moment F2 D2, and then F3 creates this moment here. If we add these three forces and place them at O, then we get this system that we see here. So from this system here, we have the resultant of the three forces, which is this resultant, and the resultant, the vector sum resultant of these three moments, we have this. And then from here, what we want to do is to create a single force, okay, by eliminating this one here. So we do the opposite of what we just saw in our previous example. So we have a single force that's placed some distance d from O. Let's see how to do that. So the steps are, first you choose a convenient point. In this case, we have already chosen O. Okay, and then you add all the forces to get the resultant R, which we have done, and this is our resultant R. Then we determine the distance d of the line of action by simply saying it's equal to the total moment divided by the resultant, which is what we see here. So this total moment divided by this resultant gives us this distance d from O. So that's the method of doing it. Now let's look at an example. So replace the force couple system of example 1 by single force from point A and determine its action distance from A. So let's remind ourselves how example 1 looked at. Like it was like this. Okay, so Rx will simply be 150 plus 150 sine 30 degrees, which is this the component going in the x. Okay, gives us 225, and then Ry is 150 cos 30, which is this component, minus 100 times 9.81 gives us minus 851.1, and then the resultant of the two is the Pythagoras of the two numbers, which gives us 88 newtons, and the angle with the x-axis, the tan inverse of Ry divided by Rx, which gives us minus 75.2 degrees. Now let's see how we can represent this in a diagram. The distance d, of course, is simply the moments at A. We calculated this in example 1 divided by this 880 gives us about 2.49 meters. Now let's see. So in our diagrammatic representation of this, we have this can be anywhere on this circle, the distance where the distance d is 2.49. Okay, but we realize that there's a specific point where it should be, and it should be at an angle minus 75.2 degrees, okay, from the x-axis, and then we place it right here. So we have now an equivalent force, okay, which is acting at 2.49 meters round about here going down, and that is our equivalent force that is equivalent to the whole system that we see here in this example. Isn't it amazing? That's it for this segment. In this video, we have covered how to calculate the moment of a force, both algebraically and by vectors. We have covered the principle of moments. We have covered the force couples and how to calculate them. We have covered force couple systems and the resultant from a point for a force couple system. Thank you for your attention.